I again would like to welcome you all to this 13 days Gyan course on earthquake seismology. We are currently running on the 8th day of this course, and we are very thankful to Professor Utpal Datta sir that he has covered so many topics so far in ground motion seismology. Apart from the mathematics that we have covered, I will basically be touching upon some of the theoretical concepts related with engineering seismology, and I will basically be having an approach where I will be talking about the notes, lectures, and also I will also touch upon some of the research topics that has been conducted by my students. And as the topic you may see on my first slide, at the very basic level, I will go through the concept of risk and hazard, and then I will cover types and scales of the zonation. Thereafter, I will briefly talk about Seismic Zonation of India. And I could, as I could understand while you were doing the lecture on surface waves, so there were some students who came to me and asking about the dispersion phenomena. So what is dispersion? That I will also touch upon. And we will also look at what is love wave dispersion, what is surface wave dispersion, what is alley wave dispersion, phase dispersion, and also what is group velocity dispersion. Thereafter, we have some of the basic idea about the surface waves, about its phenomena, about its various modes. We will also talk about some of the non-invasive techniques such as multi-analysis of surface waves and ambient vibrations, including horizontal to vertical spectral ratios. Many of the people from the audience are from National Center for Seismology, and from my research lab, from our department, and from the University of Lucknow, and from CBWS Pune. And you might have heard about this technique about horizontal to vertical spectral ratio, and as I could understand, you want to have the glimpses of this particular technique. So this is some of the pictures that I have taken from the research papers published by the Observational Seismology Lab at our department. And the first picture that you see here, on the top left corner, that is basically the site characterization map of the region of Dhanbad at some of the points in the city of Dhanbad, and we took the HVSR data at the same point where we had the standard penetration test data. So this paper was published in PGOF in 2022. Thereafter, you can see on the top right corner, there is a map of Kishanganj, that is just 100 kilometers away from here in the north, in Bihar area. That comes at the verge of seismic zone 5 and 4, and it is a PGA map, or you can say seismic zonation map at the bedrock level. I understand that today you have covered some of the concept in ground motion models, and that are also known as ground motion prediction equations, attenuation relationship prediction equations. So using those equations, you can basically generate these kind of maps. And we used a logic tree approach where we gave a weightage to various ground motion prediction equations developed by various other authors. Thereafter, we tried to come up with a better map of the area. And this research was published in Journal of Earth System Science in 2022. Thereafter, there is a map of Dominican Republic. This is the map of Dominican Republic. So, do you know where Dominican Republic is? Anybody? So Dominican Republic is in the Caribbean. It's in between the South and North America. And this map, if you look at total, then it is consisting of Hispaniola Island, which is having two countries together adjacent to each other. One is Haiti, another is Dominican Republic. And at this particular location, two plates are converging towards each other. So that is a very important zone, and 2010 Haiti earthquake came into this area. And one of my students, Mr. Sachin Kumar, was working on this particular area using the data of 23 stations, using which he developed some receiver functions. Thereafter, he used H-kappa stacking technique in order to find out the Vp by Vs ratio for the crustal part of Dominican Republic. Thereafter, he divided the entire area into the four different domains. So thereafter, you can see there is one more research figure from Mr. Dheeraj Kumar Singh. He is just sitting at the back, and he published this particular paper in PAPI, Physics of the Earth and Planetary Interior, for the region of northeastern India. So there we had the data from National Center for Seismology, and using those data we tried to find out the variations in anisotropy for a transect from north to south in the area. Similar studies was also published in GQ'd, but there we used harmonic decomposition modeling, but for the region of the Dominican Republic. I put on these figures over here just to encourage you people to go into the research and try to conduct some studies in the region of your interest. Thereafter, now the question comes, because you have been studying engineering seismology from the last 8 days, and you were trying to parameterize the hazard for a particular area using various equations in using either ground motion models or whatever probabilistic seismic hazard analysis. So one thing that should come into your mind, what is the difference between risk and hazard? Do you know what is the difference between risk and hazard? Anybody? What do you understand by hazard? And what is the difference between risk and hazard? So if I will tell you, the risk is basically the probability that a particular system or population will be affected by hazard is known as risk. I can give you an example. For example, let's suppose there is a road where there is a truck coming in and you are trying to cross the road, and the probability that you will be getting hit by the truck is known as risk. Okay. But the truck itself is known as hazard. Okay, so in the context of earthquakes, you can see that the hazard is basically the earthquake that we are talking about. And risk is what? What is the probability that there will be some casualties or the damage that we are going to have because of those earthquakes? That is your risk. And there is another term, vulnerability or seismic vulnerability. So it is basically the inherent weakness in the system. That is the vulnerability. For example, I gave you the example of the cycle that is crossing the road and there is a truck coming in. If suppose the cycle is broken, then there is an inherent vulnerability, right? So there will be more chances that it will be badly struck by the truck. So that is the vulnerability of the inherent vulnerability of the system. So risk is basically the convolution of hazard and the vulnerability together. Okay, and if you want to understand it more in the context of the earthquake, then let's suppose there is an area of California where you have several faults, long faults, and those faults are passing through some populated area, and they are also passing through some of the remotely located areas where the population density is not too high. So you can say that the fault is same, that means the hazard is same, but when it is passing through the populated area, the risk is more. But when it is passing through the remote area where the risk, where you can say that because of the population density is very sparse in those areas, then the risk is very less. There you can also have another example of Gujarat earthquake that happened in 2001. The magnitude was 7.7. It occurred a lot of casualties, around 20,000 casualties. 166,000 people were injured. There were several damages to the houses, and many aftershocks also occurred due to that earthquake. And if you compare the similar magnitude earthquake of El Salvador, happened in the same year, of having the same magnitude, the casualties were much less. 944 casualties happened only. And there was significant destruction to the houses. It may be because the population density in that area was not that much, and also the constructions were following the building codes that were designed for that area, because of which the risk was less in that area, even though the earthquake magnitude was same. Likewise, you can take an example of South Central California earthquake in 2003, magnitude 6.5, only 7 casualties were happened, 50 injured. Low risk event it was due to the occurrence in the sparsely populated area. And if you compare it with the another earthquake happened in Iran, that is famously known as Bam earthquake in 2003, the magnitude was 6.5. The casualties were much more. For example, 40,000 people died, and around 30,000 people were injured. So there was an extensive destruction in the city, and very high risk event it was due to the high population. So risk was high in case of Iran earthquake, because in Iran the structure cannot sustain the shear loading. They are basically designed to withhold the vertical loading being developed by the earthquakes. So that was the reason because of which a lot of casualties happened in the area of Iran. Now, if you look at this figure, this is the pie chart diagram that is developed after Science Council of Japan 1989, and where we are comparing several natural disasters together. Because of them, we are comparing the casualties happened because of several natural disasters. For example, earthquakes, tsunami, floods, volcanic eruptions, tropical storms, landslides, etc. So you can see more than 50% casualties in 20th century happened due to the earthquakes only. And if you look at the second pie chart, all these casualties, most of the casualties happened due to the earthquakes. Around 85% out of them happened in Asia and the Pacific region, just because the engineering design of the constructions were poor. That's why the lot of casualties happened only in the region of Asia and Pacific. However, if you will compare it with the area of Europe, America, and some part of Africa, then you can easily say that our construction in this part of the world is relatively poor if you compare it with the other part of the world. Likewise, if you look at the graph on the right hand side, that is basically the relation between the fatalities per earthquakes with respect to the earthquake magnitude, then what you will see, even the larger earthquake like Chile earthquake in 1950, Alaska earthquake in 1964, all these earthquakes were of great magnitude between 8 to 9, but still the casualties were less if you compare it with the earthquakes such as the Kashmir earthquake, or maybe the Alagir earthquake, or maybe some other earthquakes. Even the magnitude was high because these earthquakes happened in the less populated area. Likewise, if you will compare it, the most recent earthquake of Kamchatka, there in the Kamchatka region, the population was very less, and because of which you do not see a lot of casualties happen during that 9 magnitude earthquake. Okay, so what I mean to say, in this part of the world, or including India, as per the report, around 59% of the Indian landmass is susceptible to the large earthquakes. And that is why there is a need to conduct very serious earthquake hazard studies in the region. Most of the earthquake seismic zonation map that we have today, that is only at the bedrock level. We did not take into account the local specific site conditions or the secondary effect of the earthquake, such as the landslides, such as the liquefaction studies or the tsunami studies. And whatever maps we are generating, we are just generating using the regional ground motion models. We are still developing the site-specific ground motion models to have the better accuracy in our seismic zonation map. Now, if we look at this particular figure, so what do you think what this figure is all about? Do you see a map here? Right, and it is very familiar map because it is the collision plate boundary between India and Eurasia, and this boundary is around 2500 kilometers long. Along this boundary, lot of earthquake happened, lot of high magnitude earthquake happened along this boundary, and you can see we have marked all such earthquakes, not all but some of them, maybe like more than 8 magnitude earthquakes happened in this area in the history. And there are some earthquakes we have also marked, like 1905 Kangra earthquake, 1934 Bihar earthquake, 1950 Bihar Nepal Assam earthquake, 1897 Assam earthquake again, Shillong earthquake it is also known as, likewise 2001 Bhuj earthquake. So all those earthquakes are there, and the black solid circles that you see, they are representing the population centers that are available in those part of the region of India, right? So the bigger the circle is, more the population is in that area. So what you see along this plate boundary, you also notice some bubbly structures, like bubbles are there. So those bubbles are basically representing the amount of strain that was basically released after happening of those earthquakes. Okay, so in the morning today, I could see like Professor Utpal Datta sir was telling you about the gaps, seismic gaps, right? Seismic gaps are those areas along the faults where the stress is still accumulating. It hasn't released yet. So you may understand this is a 2500, right? So along this plate, right, in a one go, it will not give it. So a small earthquake or the earthquake at different location will happen, and at those locations the energy will be released. So so there are some areas that you see. So there are certain areas, for example this area here, and also this area here, and also this area here. These are basically 3 seismic gaps we have along this plate boundary. So if you look at the plate boundary, if you look at the gap in between the 1934 Bihar Nepal earthquake and also the 1897 Assam earthquake, so this seismic gap here is known as the Assam gap, and there you have another gap that is at the central of the plate boundary, that is known as the central seismic gap, and thereafter you have the Kashmir gap in between just to the west of the Kangra earthquake, that is known as the Kashmir gap. So these 3 gaps we have along this plate boundary, and these gaps are also shown in this particular picture. Okay, now look at this particular picture where we have marked the epicenter location on the Indian subcontinent map. This map is basically taken from Walling and Mohanty. The paper was published in 2010. And what you see here, along the plate margin, all along the plate margin, there is a cluster of earthquakes. Okay, so along the plate margin, most of the earthquakes are happening, and you see a sparsely located earthquake epicenter in the peninsular India. Right. So in the peninsular India, the earthquakes are happening, but not as much as it is happening at the boundary location. Right. Even if you look at the northeastern India, there is a very high frequency of the earthquake you see, and you also see a clustering of the earthquake in the Bihar Nepal border, and also in the northwestern Himalaya, and also in the northern Himalaya, along the Hindu Kush region, along the Kirthar Suleiman ranges, and in the Indo-Burma ranges, right? So if you compare this density of the earthquakes with the peninsular India, it is much more high. But it doesn't mean that the earthquakes that are happening in the peninsular India are not equally damaging as those of the earthquake happening in the northern Himalaya or the northeastern Himalaya, because in the region of peninsular India, people are not well prepared to the devastating effect of the earthquake. So when they construct something, they do not take into account the engineering design of the construction that might withhold the devastating effect of the earthquakes. Just to explain you better, I also put in the map of the northeastern India, and in this map of northeastern India on the right, you see there is a network of fault. Most of the faults are thrust faults like MCT, MBT, and the main frontal thrust, that is the younger thrust fault system. And thereafter you have in the northeastern region, you have the Indo-Burma ranges, and also you have the basin, Bengal basin, which has a very thick pile of sediments of around 18 kilometer depth, which is considered to be the largest in the world. And thereafter you have Sundarban Delta. You also have Shillong Plateau, and Shillong Plateau have witnessed a very large earthquake in 1897. 1897 earthquake has caused a lot of casualties in the region, because of which soon after the happening of the earthquake, the systematic study of the earthquake has started to happen. And there is a lot of geological complexity in the region. A lot of earthquakes are happening. As we know that, we record those earthquakes on daily basis. National Center for Seismology has already installed around 27 stations in the region, and they are trying to increase even more. And if you look at this region, most of the world scientists are very interested to decipher the mysteries associated with the geodynamics of this region. And for that purpose, they have been installing a lot of arrays, like in Bangladesh, also in Burma, and they are also requesting the Indian government to install some more seismometers in the region. If you look at the geodynamics of this region, then Shillong Plateau was uplifted in 1897, because of which the theory of pop-up of the Shillong Plateau was evoked. And if you there are a lot of controversies about the earthquakes happening in the region. Some people believe that the earthquakes are happening maybe due to the collision that is happening in the north. There is no earthquake happening underneath the Indo-Burma ranges due to the subduction. So basically they thought that the subduction has stopped, and most of the seismicity that you see in the northeastern India is basically due to the collision happening in the north. And there are some people, those who say that the subduction is still active, but most of the seismicity is happening due to the pop-up of the Shillong Plateau. And there is like, if you look at the Shillong Plateau region also, which is the location of the 1897 Shillong earthquake, a lot of casualties happen, and still we do not know the proper reason why that earthquake happened. Some people says that there might be a possibility of a fault that is not visible at the surface, and that is a blind fault located at the northern periphery of the Shillong Plateau. But there is the other section of scientists who believe that the Oldham fault is not located right at the northern periphery, but it is little far away from the northern periphery of the Shillong Plateau, and it is basically known as the Brahmaputra fault. Now, if we go further, so what do you think what these figures are? This is the seismic zonation map. Very good. So this is the seismic zonation map of some study region. The right one you can easily figure out. It is seismic zonation map of India, and it was published in 2016 by Bureau of Indian Standard, which is almost similar to the map that was published in 2002. Now, if you look at the left-hand side map, this is the map of seismic zonation using probabilistic seismic hazard analysis for the Kishanganj that I just told you about, and we predicted the PGAs for this particular region, and the PGAs are color coded in between red to green. Green being the least vulnerable and red being the most vulnerable region in the Kishanganj. And the Bureau of Indian Standard 2016 published this map for India, where they divided the entire entire subcontinent into the 4 distinct zones, starting from 2nd to 5, and second being much of the region in the Deccan area and in the peninsular Indian region, and zone 5 for the most of the northeastern and the Kashmir region, or maybe the Gujarat region. Now, so this kind of zoning we are basically interested about in this particular course that we would like to see. So like this is a very important thing, because recently Ministry of Earth Sciences has floated a project to particularly do the zoning of 10 cities that they want to convert into the smart cities, and Dhanbad is one of them, fortunately. Okay, now the question comes, what are seismic zones? Okay, so seismic zones are basically, you are trying to delineate the region into several smaller parts having the potential of earthquakes or earthquake hazard. Okay, so seismic zones basically, or seismic zoning can be done at the national level, at the regional level, or at the site specific region. And when we do the national or the regional zonation, we do not take into account the local or the secondary effect of the earthquakes. So local effect means you do not take into account the local site conditions, or you do not characterize the soil, you do not take into account the site amplifications of that area. Okay, and you also do not take into account the landslide effects, also the liquefaction effect, also maybe the tsunami modeling you don't do for that area. You just produce those maps at the bedrock level. Okay, so today in the previous class, maybe you are going to approach towards conducting the probabilistic seismic hazard analysis or the deterministic seismic hazard analysis. Using those techniques, you are basically trying to find out the PGA values at the bedrock level. Okay, so I can't write actually. So basically what we are trying to do is, let's suppose there is this surface. Okay, surface, this is your surface, and here you have the bedrock. Right, so any area you will go on, if you will dig little bit into the ground, you will encounter some soils, and thereafter you will encounter some solid rocky surface after a certain depth. That we generally call it as a bedrock. Okay, and if suppose you do not have any bedrock in an area, if you do not dig that far, then around 700 meter per second, if the velocity is there of the shear wave velocity, that we call it as an engineering bedrock. Okay, so this is your bedrock here, bedrock. Okay, and what you are basically doing here, let's suppose there is an earthquake here, and from the earthquake you have some energy coming in, and that will come at the bedrock. Okay, how much motion it will occur at the bedrock level, that you are trying to find out using the DSHA or the PSHA technique, right? And thereafter, if you want to find out what is the motion, what is the resulting motion from the bedrock to the surface, how much energy is going to transfer from the bedrock to the surface, then you would like to do more kind of operations. So in seismic zonation or seismic, to be very specific, in the seismic micro zonation, you follow certain steps. First, you do seismic hazard analysis. In the seismic hazard analysis, you are trying to find out what is the motion at the bedrock. So at this level, you are trying to find out. So that is what I said, like most of the maps that we have today in India at the regional or the national level, those are at the bedrock level. Only at the bedrock level, you are going to know what will be the ground motion in the near future. Okay, so Now the task comes how to convert these map at the surface level. So for that purpose, you know there is in between there are some soil layers, right? So you need to find out how much energy that is coming to the bedrock, that we call it input motion, is going to transfer to the surface, because it will go through the soil layers, right? So if they are going through the soil layers, then there should be something that we should know about the soil in order to know how much amount of energy is being transferred to the surface. Okay, and that particular thing that we want to know is known as the transfer function. Okay, for knowing the transfer function, first you need to conduct seismic site characterization. Okay, you need to characterize the soil using some kind of techniques, or maybe you can use invasive techniques or non-invasive techniques. Okay, so you can conduct like a standard penetration test, cone penetration test, or maybe some other test, or maybe you can do the MASW testing, multi-analysis of surface wave, horizontal to vertical spectral ratios. So using those methods, you are basically trying to find out the shear modulus or the shear wave velocity of the soil. Okay, using that shear wave velocity or the shear modulus, you are going to conduct the site response study. Okay, so the first step that you are going to do is seismic hazard analysis, in short, which is also known as SHA. Okay, and in that particular section, in that particular step, there are two things you can do. Either you can use the deterministic seismic hazard analysis, that is also known as DSHA, or there is another technique that you can do is PSHA. Okay, you are going to conduct the seismic site response study or the site response study. Using site response study, what you are going to find? You are going to find the transfer function, and using that transfer function, the transfer function will be a single number. Okay, and then you multiply that number with the input motion, and then at the surface you are going to get how much amount of the energy is being transferred to the surface, right? So this is what we are required to do. Thereafter, if suppose the area is prone to landslide or the slopy area is there, then you can also conduct landslide study. If the area is prone to liquefaction, then you can also conduct liquefaction study. If the area is near to the shore, then you can also conduct the tsunami modeling study. So you can see there are 6 steps, 6 major steps. One is seismic hazard analysis. Second is seismic site characterization. Third is site response study. Fourth is landslide modeling. Fifth is liquefaction study. Sixth is tsunami modeling. And thereafter you do all these steps. You need to integrate them together in order to find the final value of the hazard. Okay, so final steps will be known as integration of the hazard. Okay, so in the seismic zonation, we are basically going to we should perform all these steps, but due to the lack of the data or due to the lack of maybe the instrument, you do not have enough information or you do not know about the geology of the area, then you basically compromise upon to the macro zonation mapping or maybe some other kind of mapping where you do not require. So that is why you have the maps developed for India for the bedrock level. But the efforts are undergoing and we are moving towards generating better maps for the Indian subcontinent. So if we talk about the seismic zones, so seismic zones is basically you are dividing the entire area into different number of zones where there is a potential effect of the earthquakes. Okay, so it can be done at national level, regional level, local level, or site specific studies you can do. And if we talk about the national or the continental level or maybe the regional scale study you want to do, so it is sometimes not possible that you are going to do the local site specific testing at each of the point of the study area. Okay, that is why you compromise with only the bedrock level maps, and then you do not consider the effect of the landslides, liquefaction and other studies you may conduct in the area for the better hazard planning. So zoning assumes uniform hazard parameters within each zone, though actual risk varies continuously. So if you look at the zoning of India, only 4 zones are identified, starting from 2nd to 5th. Okay, so for zoning purposes, you need to have minimum number of zones, because you want to have the simplified representation of your hazard value. Okay, higher the number, it will become more complex, right? That is why, but it doesn't mean that within those zones the hazard value is not varying. It is actually varying, but you are basically taking the most disastrous scenario in order to find out that particular value of the hazard in that particular region. So, so a seismic zone is an area with fairly consistent seismic activity, sometimes called as seismic hazard zone, for areas with higher risk. One thing I want to clear, do not confuse seismic zoning map with the seismicity map. Okay, sometimes I see the student coming to me and then asking me the question, sir, what is the difference between seismic zoning map and the seismicity map? Okay, so seismicity map is just, you are going to mark the epicenter of the earthquakes within a particular period on a particular map. So it just represents the clustering of the earthquake epicenter. Okay, it is not the zoning. In the zoning map, you are basically trying to identify the regions with the potential hazardous value of the earthquake using peak ground acceleration, peak ground velocity, or maybe peak ground displacement. Okay, and while you conduct any seismic zoning study, you need to have inputs from the geologist, from the seismologist, from the geotechnical engineer, from the earthquake engineer, or the structural engineer. So geologist will basically tell you about where the source is located, what kind of fault it is, what is the geometry of it. All those information will be given by the geologist, while the seismologist will basically give you the record of the earthquake, the catalog, what is the magnitude, what other information of the earthquake is available, he will give you. Thereafter, you have the geotechnical engineer. He will tell you about the soil conditions in the area. He will perform some kind of testing, or maybe the mass payload testing, or maybe the standard penetration testing, or maybe the cone penetration testing. And using all these information together, you are going to perform the zoning of the area, and the final zoning map you are going to hand it over to the structural engineer. Okay, so the structural engineer will take that into account and will make some building codes for the people, so that they can take those things into account in order to construct a better building that may provide some resistance to the earthquakes. Now, I think you have seen this map before, right? This is the seismic hazard map, global seismic hazard map. Sir has also shown you this map, right? So you can see this is also color coded, the white being almost no, it is almost not susceptible to the devastating effect of the earthquake, and the brown being very high vulnerability due to the earthquake. Okay, so you can see the plate margins are all basically having the darker red or brownish color. So this is the zoning map of the world. Now, the question comes, as I explained it to you, like what is the need of seismic zonation? So seismic zonation basically identifies the region of varying level of the potential ground shaking, and that is based upon the historical data, or maybe it can provide you some future projections. Okay, so you might see in the seismic zonation map, when you will develop the probabilistic seismic zonation map, they will say that there is a probability of exceedance of maybe 0.64 of having this much of PGA values that may be exceeded in next 50, 100 years, or maybe 500 years. Okay, so that is basically the probabilistically you are saying that in these many number of years, this particular PGA value in this region is going to be exceeded. Okay, so this information if you will provide to your engineers, then they may take that information into account and then try to develop their building codes accordingly. So these maps are used to inform seismic design codes and the construction practices, enhancing structural safety. Zonation helps reduce earthquake-related human economic losses, contributing to long-term economic and the political stability. It also provides critical input for land use planning by highlighting vulnerable areas and incorporating local soil conditions through amplification factors improves the accuracy of hazard assessment. Okay, so all this information is needed for all these purposes. Now, what are the types of zonation? Okay, there are basically three types of zonation. First is macro zonation, second is micro zonation, and the third is nano zonation. Okay, nano zonation is very rigorous zonation, and that is very impractical so far. But we can talk about macro zonation and micro zonation. So macro zonation is basically done at a broader scale, at the continent level, at the country level. Okay, in this particular zonation, you take into account the seismic activity, geological features, and you do not incorporate much about the geotechnical data. Okay, so that is so macro zonation is the zonation which is a simpler kind of zonation where you are just taking into account the broader features like the seismic activity, seismicity of the area, or maybe the geological features. Okay, and it involves dividing the territory into zones based on the anticipated seismic intensity over different return periods. Okay, so it basically take into account the seismic intensity, historical seismic intensity, maybe some verbal historical records are available in some literature survey, that also it may taken into account. So seismic zonation maps basically parameterize the seismic intensity or maybe the peak ground acceleration or maybe some other strong ground motion parameters. For large regions such as continent or countries, macro level zonation is applied, because for the larger regions such as the country of India or maybe some other country, if you are going to go for site specific study taken into account of the local soil condition, that will be a very tedious task. So for that purpose, macro level seismic zonation is preferred. Number of zones created in micro zonation. Macro zonation is not fixed and can vary depending on the chosen criteria or the objectives. Now here comes the micro zonation. Okay, in the micro zonation, you take into account the several factors or several input parameters provided by geologists or maybe seismologists. Geotechnical factors you also take into account, and you also may be taking into account the soil conditions for which you are going to conduct the site specific seismic site characterization study, and also you will conduct the seismic site response study in order to find out how much bedrock motion is going to be transferred at the surface. Right. So now, so micro zonation offers guidelines for suitable type of new constructions in specific areas and provides insights into the potential vulnerability of the existing structures to seismic activity. And seismic macro zonation involves detailed mapping of all potential earthquakes and related hazards within a region. It subdivides the area into zones with similar level of exposure to earthquake effect. So the first seismic microzonation study was conducted in Japan in the city of Yokohama in 1954, where they basically classified the entire area into different number of zones based on the soil conditions and established seismic design coefficients that may tailor to various type of structures within those zones. Now, so that I told you, it is a very rigorous type of zonation, nano zonation, and this kind of zonation is considered to be very impractical so far. So now if we move further, we will concentrate upon micro zonation. So there are basically three types of micro zonation. One is grade 1, another is grade 2, third one is grade 3. So grade 1 is the general zonation or general microzonation. Grade 2 is the detailed microzonation. Grade 3 is the rigorous microzonation. Okay, so you can see on the steps the general zonation that has the scale of 1 to 50,000 to 1 to 1 million. So basically 50,000 on the ground is equal to 1 onto the map. Okay, or maybe 1 million onto the ground is equal to 1 on the map. Okay, so you can understand that that is a very simplified zonation that comes within the micro zonation. It is also similar to macro zonation that we do. Okay, so in this particular zonation you do not take into account various soil factors or maybe site response study. So this is why it is known as general zonation. Now if there is a detailed zonation, the scale is 1 to 10,000 to 1 to 100,000. Okay, likewise if you go for much better resolution, then rigorous zonation you need to do, that is grade 3, and it comes into the scale of 1 to 5,000 to 1 to 25,000. Okay, now what is grade 1? So as I told you, it is similar to national level macro zonation studies. Okay, and the input data that you require for grade 1, that is your general micro zonation study, is the seismological record. You are going to use the regional attenuation relationships. What are the attenuation relationships? Anybody? So attenuation relationships are similar to the ground model, okay, ground motion models, and that basically give you the information about the strong motion parameter as a function of maybe magnitude, maybe distance, or maybe some attenuation factors, or maybe some other parameters that you may need to include. So regional attenuation, so basically in order to have a better seismic zonation map, you must have to have a site specific or the locally developed attenuation relationship or ground motion model. But in this kind of general grade 1 micro zonation mapping, you are not going to have that. You are going to use the regional attenuation relationship. So basically you can use Cornell et al. Equation that was developed in I think 2000. I may not be right about the year. Okay, or maybe Joyner and Boer you can use. So Joyner and Boer was the equation which was used in the GSHAP mapping, like Global Seismic Hazard Assessment Program. It was done by Bhatia et al. In 2000. So they used the regional attenuation relationship, and or you can use the attenuation relationship for a particular area that is similar to other area. So similar kind of study that might be conducted in a region, and you are going to conduct the study in your area of interest, and the geologically both are similar, then you can use the same attenuation relationship. And in this kind of grade 1 seismic micro zonation mapping, you are going to estimate bedrock input ground motions. That means at the bedrock level you are going to generate your mapping. Site effect are generally estimated from the existing geological and the geomorphological maps. You are not going to do site specific testing, or you are not going to conduct any testing on the soil, or invasive or the non-invasive techniques you are going to use, and direct geophysical geotechnical investigations are rarely performed. So this is what I was saying. So like you are not going to perform the geophysical investigations, okay, and even if you are doing, it is rarely performed. Okay, so not suitable for urban centers due to limited detail and lack of site specific investigations. Okay, it is recommended only for low seismic hazard zones. So you know, like in the area where the potential for the earthquake is very low, in that kind of areas you can perform such kind of zoning, the grade 1 zoning. Okay, or you can perform this kind of zoning in a very low population area or the very low population density. Okay, mapping scale typically ranges from 1 to, as we have already discussed, 1 to 1 million to 1 to 50,000. Now if we talk about grade 2, grade 2 basically takes more input more elaborate input if you compare it with the grade 2, grade 1. Here you are going to use seismological data and models. You are going to use the specific attenuation relationships or recurrence relations. You are also going to use the geotechnical data and the report of the geotechnical studies, and also you are going to use the you are going to validate the collected data and the available data. Okay, so if I could remember, like as I told you, the Dhanbad comes one in the seismic zonation project of Ministry of Earth Sciences. So a team from NCS came over here in Dhanbad and they were conducting like standard penetration testing at various sites of Dhanbad, and they were staying here for a duration of maybe more than 10 days and were collecting the data. So they were basically here to collect the soil specific parameters. For example, so they were doing the soil testing. So they were basically conducting MASW testing, multi-analysis of surface wave, where they were trying to basically generate shear wave velocity model in order to find out the shear modulus of the soil. That may basically be used for the site response study to find out how much motion from the bedrock has been transferred to the surface. Okay, so now laboratory studies you can do in this, and also the field and the experimental studies. This level of microzonation is to be adopted for the regions in higher seismic hazard, zone 4 to 5. Okay, with less population. Okay, the population may be less, but the area is more susceptible to the devastating effect of the earthquakes or more prone to the earthquakes, then it may be conducted in those kind of regions. For the regions with moderate seismic hazard, that means zone 3, but with population exceeding 100,000, then this can be adopted. Okay, even if the region is coming into the zone 3 but the population is high in that area, then this kind of grade 2 microzonation can be conducted for that area. And the scale of the study and the mapping is larger than the previous level of microzonation. International Seismic Society of Soil Mechanics and the Geotechnical Engineering ISSMGE recommend a scale of study and mapping is 1 to 100,000 to 1 to 10,000. Okay, so now if we talk about grade 3, that is more rigorous kind of seismic microzonation. So this level of seismic microzonation is adopted for highly vulnerable areas. Okay, for example zone 5 and also the population density is very high, then this kind of grade 3 seismic microzonation may be conducted in that area. Okay, in this particular zonation you need to have the rigorous inputs from geotechnical studies, from geophysical investigations. You also need to have the value of the peak hazard amplitude, peak horizontal amplitude values need to be evaluated using PSHA technique, probabilistic seismic hazard technique. Okay, and you also maybe need to perform the secondary effect of the earthquakes analysis. For example, liquefaction hazard analysis, landslide effect analysis, tsunami modeling you may have to do for the area. So the output of this kind of grade 3 seismic microzonation mapping would be like site classification map you will get. Okay, you are going to classify the site. Okay, and then you may also be generating the maps for the peak horizontal acceleration, spectral acceleration values at the bedrock level, and also you may be trying to map the area in terms of the spatial variation of the peak horizontal acceleration and the spectral acceleration values at the surface level. Liquefaction hazard map you may get. You may also get landslide and the tsunami map, and then if you will integrate them together, you will be having the comprehensive seismic hazard map by combining all the above given maps. Okay, so this is what you need to. So all in all, if you look at the steps of the seismic microzonation, so seismic microzonation steps look something like this. Is it visible? Okay, so if you look at the middle column, so it is starting from seismic hazard analysis. Okay, as I just explained, you are required to do seismic hazard analysis. Okay, the first step of seismic microzonation. So in this hazard analysis, you are going to find out at bedrock how much motion is occurring. Okay, so you can do it in two ways. Either you can do it deterministically, that means you are going to find out a controlling earthquake, because if suppose there is a region which is surrounded by several faults, then you need to find out using which fault and which earthquake the most or maximum PGA value at the site of interest is occurring. You need to find out the maximum PGA value because of which fault or the source is occurring at that particular site of interest. So using that earthquake only, you are going to find out that what is the value of the hazard. That is you are doing using by finding the controlling earthquake. That is your deterministic seismic hazard analysis. And then you have the probabilistic seismic hazard analysis. You are not only finding the controlling earthquake, but you are trying to integrate the information from all the earthquakes available, and then probabilistically using total probability theorem, then you are trying to find out the probability that how much time frame is there that a particular value of hazard will be exceeded in a particular area. Okay, so that is what you are doing in seismic hazard analysis. So seismic hazard analysis, the inputs are geology data, you have the catalog data, you have the tectonics of the area, you have the geophysical data, maybe remote sensing data, and the regional attenuation relationships. Okay, all these informations will be put in as an input to the seismic hazard analysis. Okay, now the output, if you look at, so if you are doing it deterministically, then the output will be, you may be able to find out the controlling earthquake, okay, because of which the largest value of the PGAs are occurring at a particular site. That is your maximum credible earthquake, that is also known as. Okay, then because you are going to do this analysis, then because at the bedrock level you are going to find out what is the value of the PGAs are occurring, then based on the PGA value you can also find out like what is the vulnerability of the area. Where there are the more PGAs, the area is more vulnerable, right? And also you can do the synthetic ground motion modeling. Okay, using the bedrock motion, you can synthetically find out what is the value of the hazard at the surface. So synthetic ground motion model you can find out. You can also find out hazard parameters in terms of PGA, PGV and PGD. So all these things you are going to find out in seismic hazard analysis as an output, right? And then after that you find out the value of hazard at the bedrock level. Then in order to find out the value of hazard at the surface, because that is our aim, right? So if you want to find out the value of hazard at the surface, you need to find out what is the elastic parameters associated with the layers in between the bedrock and the surface, and those are the soil layers. Okay, so for the soil layers, in order to find out the elastic parameters, you need to perform site characterization. Okay, you are going to characterize the soil layers in between. Okay, so in order to do the characterization, you are going to perform some geotechnical modeling or geotechnical data you need to collect. Okay, or maybe you need to do some geophysical surveys. Okay, like HVSR, MASW. Okay, and you may also need to do the soil mapping. Okay, so when you do the site characterization, the output would be, you will be having maybe if you are doing SPT surveys, standard penetration test, where basically you are just digging a borehole, and at each depth you are taking a sample out, okay, and then doing some testing in the lab, or maybe you are trying to find out the blow counts, how many blow counts are required at each level of 45 centimeter, and then finally wherever there is a refusal depth, then you are saying, okay, this may be the value of blow count or SPT blow count value, and using which that blow count value, you are going to estimate empirically what should be the value of shear wave velocity. Okay, so SPT blow count corrections you may find out. You may do the shear wave velocity mapping, or maybe the VS30 mapping, or the standard SPT blow count values. Actually इस टाइमर बंद करना पड़ेगा. Okay, Now, thereafter you may perform site response study. In site response study, there are several techniques that you may perform. Okay, maybe you can do linear site response analysis, you can do equivalent linear site response analysis, or maybe non-linear site response analysis. Okay, basically you are trying to follow the trajectory of the strain stress curve in site response analysis in order to find out the amplification factor or the transfer function of the soil. Okay, thereafter you can do other kind of assessment like liquefaction assessment, landslide assessment, or maybe tsunami modeling, and finally you can integrate all the steps together to find out the final value of the hazard. Okay, now these are the steps of seismic microjonation. So now we can talk about what is the microjonation and the codal provisions in India. Okay, so most of the earthquake I told you are happening because the Indian plate is drifting towards the Eurasian plate, and when it is drifting towards, then there might be interlocking happening at the collision plate boundary, and when the interlocking is happening, the stress is getting built up, and that stress is basically generating the strain, and when that strain goes beyond the elastic limit of the rocks present over there, then the earthquakes are happening. So those earthquakes are happening because of the sliding of the tectonic plates. Okay, so it is also said that the 60% of the Indian land is basically experiencing the shaking of intensity 7 or higher on the modified Mercalli intensity scale. Okay, if you talk particularly, then the Himalayan region is most vulnerable to the major earthquakes, and it may also experience the earthquake of magnitude 8 or more than 8 magnitude. Okay, if you look at the earthquakes happened so far, like Assam earthquake 1897, Kangra earthquake 1905, Bihar Nepal earthquake 1934, and Assam Tibet earthquake in 1950. These are few of the earthquakes that we know so far, but because you know in the past many other earthquakes has happened along that plate margin. Okay, now so Dr. Thomas Oldham, who is the first director of the Geological Survey of India, he basically laid the foundation of the scientific studies of the earthquakes in India. Okay, and he compiled a very well-known catalog of Indian earthquakes and carried out investigation of the Kachar earthquake in 1869. Thereafter, following his legacy, his son R.D. Oldham also went on to become the director of GSI and also contributed very significantly to the earthquake studies. He also wrote a memoir of the 1897 Assam earthquake, and which was considered by Richter as one of the most valuable source book in seismology. Okay, Indian subcontinent as per IS 1893-1984 can be classified into 5 seismic zones, and the increased seismic activity during the last 2 decades forced the reclassification of the 4 seismic zones that we will come towards later. Okay, now the seismic zonation map, you know, like currently we have 4 seismic zones starting from 2 to 5. So if we look at the seismic zonation studies in India starting from 1962, so in 1935 there was an earthquake happened, Bihar Nepal earthquake, and after which Geological Survey of India published a map, seismic zonation map, which was basically based upon the intensity recorded by the various earthquakes along the Indian subcontinent. So they prepared a map, and which was basically also published in 1962. Okay, and thereafter the historical record of the Indian earthquake was basically incorporated for the 200 years in that particular zoning map, starting from 19th century, mostly from the newspaper descriptions of what happened at different places during a particular earthquake. So mostly due to the newspaper descriptions, verbal annotations, and they tried to incorporate the information of the historical earthquake, and then they come up with the seismic zonation map of India. So 1935 there was an earthquake happened in Quetta, that is also known as Quetta earthquake, and it was a very interesting earthquake from several viewpoints. And for the first time after this earthquake, a systematic and the serious studies happened, and soon after this GSI published a map, as I told you, in 1935 after the 1934 infamous Bihar-Nepal earthquake. Okay, in 1962, Bureau of Indian Standard published the Seismic Zonation Map of India, which is also called as BIS 1962, and that is mostly based upon the earthquake epicenter and the isoseismal maps published by GSI in 1935. So if you look at this particular zoning, then they considered 7 seismic zones. Okay, and zone were starting from 0 and going up to Roman letter 6. Okay, and they were based upon the modified Mercalli intensity scale. Below 5 considered as 0 zone, and if the intensity was 5, then Roman letter 1 zone. Likewise, it was going on. As per this, the earthquake of magnitude 5 and above with maximum MMI scale ranging from 5 to 9 was considered. So you can see on the right hand side, below 5 and above were considered in this particular zoning map of India. Now, as per this zoning map, the Deccan Plateau was considered to be the stable continental region. That means it was considered to be a safe zone. Okay, so safe zone means there was a expectation that no earthquake will ever happen in this region. Okay, so that is why it was assigned 0. Okay, while a larger part of the northeastern India was assigned Roman letter 6. That was the most vulnerable region that was considered in this particular zoning map. So you can see on the left hand side, this is the 1962 map published by Bureau of Indian Standard. So you can see most of the peninsular India coming into the safe zone and assigned a 0 mark. Okay, and northeastern India and some part of the northern India were considered to be the most vulnerable. Okay, and then this map was revised in 1966, and in 1966 they have also basically considered some more parameter, and they have squeezed the 0 region further to the south of the Nagpur, and then came up with the new map in 1966.